we're going to take a look at two stars orbiting each other, also known as binary stars. We used to think this was pretty rare, but it turns out this is much more common than we originally thought. In fact, about half of all the star systems that we see are binary star systems, which means there are at least two stars that are orbiting around each other, which means that 3 out of every 2 stars that we see in the night sky are a binary star. I'm going to let you guys think about that one. It's also very difficult to figure out a star's mass if it's all by itself. But if we have 2 stars orbiting and we can see them orbit, it's very easy and straightforward to measure a star's mass, which means virtually every piece of information that we know about a star's mass comes from binary star systems. And if you remember, a star's mass is what tells us virtually everything else about the star. A star's mass is what tells us virtually everything else about a star. So these binary stars that we see up in the sky are extraordinarily important to figure everything else out about stars. What is the definition of a binary star? It is 2 stars that are orbiting each other. They're actually both orbiting around a center of gravity, which is usually in between the 2 stars. And from what we've seen, virtually every single big giant O-class star or B-class star is actually a binary star system, which means it has a little tiny friend next to it. About 50% of all stars that we've seen end up being a binary star. A couple quick facts that you guys are going to need to know. Binary stars orbit around each other at all different orbital periods, ranging from a few seconds or minutes up to thousands of years. Any type of star can be a binary star, OBAFGKM, supergiants, white dwarfs, any type of star, any mass star, any size star can be a binary star. They can have very circular or very elliptical orbits, which means that there is a lot of variation in the types of binary star systems that we see. We're pretty sure that most binary star systems, the 2 stars form at the same time out of that same stellar nebula, that same cloud of gas and dust. It's not like one star is passing the other star and gets trapped by its gravity. So we're pretty sure that they both form at the same time, though we do have evidence that sometimes one star will capture the other, but most of them that doesn't happen. If the stars are right next to each other, they could share material, which means one star might get more mass, one star might have mass taken away from it, which is going to affect how hot they burn, how fast they burn. It's going to affect their evolution throughout their lifespan. It's going to affect how they die. And those stars that take thousands of years to orbit around each other, they are so far away from each other, they for all intents and purposes act as though they are a single star system. And I added one last little note down at the bottom. If a binary star system has planets, the stars are orbiting like this, the planets are going to orbit way far out, orbiting those 2 stars as if it was a single object. So the stars are in the center of that solar system, and then the planets are going to orbit around both of the stars. If the planets tried to do a figure 8 and kind of weave in between the stars, they would get slingshotted out virtually immediately. So if a binary star system has planets, they actually orbit way far out. They would orbit just like this. This is an actual photo, a real-life photo of a planet orbiting 2 binary stars from way far out. When you look up at the night sky, you may see 2 stars that are right next to each other. And a lot of people think, oh, because they're right next to each other, they must be binary stars. A lot of times what you're actually seeing is called an optical double. It's basically an optical illusion. It's where 2 stars appear right next to each other, but in reality, they're very far apart from one another. So we have to be careful when we are looking for binary star systems that it's not just an optical illusion, what's known as an optical double, where they appear next to each other from our point of view. But there are many examples of actual binary star systems, and there are different types. There's visual binary system, there's spectrum binary, spectroscopic binary, astrometric binary, and eclipsing binary. I'm going to pause here so that you can write down the definitions, and then I am going to explain what each one of these means. So a visual binary is simply a binary star system where you can see both of those stars, usually with a telescope. Down here are a number of examples of visual binaries where we can see both stars through a telescope. Usually, though, one star is going to be much brighter than the other star. So we have to look very closely in order to see the dimmer star, because the brighter one is going to way outshine the dimmer one. Very similar to how a star can outshine an exoplanet. Well, one star, like Polaris or Rigel, can outshine their little tiny friend. Sometimes you get a trinary star system, where you have 3 stars. This little slideshow could go on all day because we have a whole bunch of examples of binary star systems. Half the stars up there are binary. An astrometric binary system is where we might only see one star, but because it is wobbling, we can infer that there is another star there. You might remember this is also how we find some exoplanets. Well, one exoplanet. And the reason that we think that's an exoplanet and not a star is simply by how much that star is wobbling. If it's wobbling a lot, we know that it's something with a lot of mass causing that wobble, and it's a star. If it's wobbling a little bit, then it's a small mass, is going to be a planet. So even if we cannot see the other star, if the brighter star is wobbling a lot, there has to be something with a lot of mass there, and it's either a planet, a star, or a black hole. And we can usually figure out which it is simply by looking at how wobbly this star is. That will tell us the mass of the other object. A good example is Sirius A and B. Sirius, the brightest star in the night sky, if you look closely, has a little wobble. And it has a friend, Sirius B, which is a white dwarf. And remember, white dwarfs are so hot, they actually put out light in the X-ray part of the spectrum, so they're very hard to see with a visible light telescope. All the way back in the 1800s, we noticed that Sirius had a wobble. We assumed that there was something causing that, another star causing that. So Sirius actually started out as an astrometric binary, and once we found Sirius B, its little white dwarf friend, then it turned into a visual binary because we could see the other star. It's actually kind of cool that if you look in visible light, Sirius A is much brighter, the brightest star in the night sky. Sirius B, the white dwarf, is very dim. But if you take a look in X-rays, Sirius B, the white dwarf, way outshines Sirius because white dwarfs give off a ton of their energy in the X-ray part of the spectrum. Depending on which telescope you use, you're going to get much different images giving you different information. An eclipsing binary, this is what's happening over my head, and this is when the 2 different stars are orbiting on our line of sight. And so one star is going to seem to go in front of the other star, and when that happens, the brightness curve is going to change. This is very similar to how we find exoplanets. Based on how much it dips, as well as how often it dips, we can figure out how far apart they are, and then from there figure out the mass of each one of those stars. And that lets us gain all sorts of information about other single stars by comparing it to these binary systems. I want to go over this because you're going to see this on a test. Let's look at this middle example here. You have a bright blue star and a dim red star. This bright blue star is going to go in front of the dim star, and because the dim one is being blocked a little bit, the light curve is not going to dip very much. However, when the bright star goes behind the dim star, well, then the only thing that we see is that dim star, and the light is going to dip a lot. Just like we had a bunch of information about exoplanets using light curves, we get a bunch of information about stars using light curves. A lot of the ways that we find these binary star systems mirror or are exactly the same as the ways that we find exoplanets. The next one is a spectrum binary. If we see a spectrum that doesn't make sense, maybe it's because there's 2 stars there. So a very, very hot star usually has a lot of hydrogen lines, these very skinny ones. Cooler stars have much more metals or elements bigger than hydrogen and helium. If we see 2 of these spectrums that are combined together, then we know that there's most likely 2 stars giving off that spectrum. So while we can't necessarily see each star individually through a telescope, we can tell that there are 2 different spectrums coming from the same point in the sky. It must be 2 different stars. That's what's known as a spectrum binary, because we use their spectrum in order to figure it out. And finally, this one sounds very similar. This is a spectroscopic binary. And a spectroscopic binary is when one star is orbiting another, and it's coming towards us and away from us, and then towards us and away from us. And just like the radial velocity technique, we use the Doppler effect. And you can see that as these stars orbit around each other, their spectrums are going to be redshifted and then blue shifted, and then redshifted and then blue shifted. How often that happens, as well as how much it is redshifted and blue shifted, that's going to tell us their distance and orbital speed, and we can then figure out each star's mass. So astrophysicists love finding binary star systems because they can almost always determine the exact masses of both stars. And when they have the mass information from tens of thousands of binary star systems, they can then extrapolate that out for when we find individual stars. If we have an individual star and then a binary star over here that are very similar in their brightness, in their size, well, we can use that information from the binary star system, extrapolate that out, and now we know a bunch of information about this solitary star. Just like we miss probably a lot of exoplanets, we're also probably missing a lot of binary stars. A lot of the stars that are up there are probably binary stars, and we don't even realize it because our methods of detecting them either aren't good enough, we don't have good enough equipment yet, maybe the line of sight is wrong. There's a lot of reasons that we might not be able to detect whether or not something is a binary star system. But binary stars are the fundamental way that we know about stars and their masses. And remember, mass is the most important thing to know about a star. So if it wasn't for binary stars, we would know very, very little about any stars up in space. Binary stars for the win.